slice here would be much harder. Those of you, I think everyone's aware of, you're here. He founded RStudio almost 10 years ago.
All right, thanks, man.
And this is revolutionized the way we use R. People are using R for a long time as copy and paste from a text editor into R. If you had a text editor, you didn't have a debugger, a visual debugger, you have a lot of these nice things that makes life so easy. So before he even goes on, I think we all owe a huge debt of gratitude to JJ. And let's give him an embarrassing round of applause. So I bring you the man who has changed all of our lives.
That's a lot of pressure. Thanks, Jared. Let me see if I can get the, is the mic working okay? Good? Okay, great. All right. Tonight we are going to talk about, after I get my password entered here, let's see. Boom. We're going to talk about machine learning with TensorFlow and R. Some of you may have heard of TensorFlow. It's an open source library from Google. It came out a little over 2 years ago. And from the time that TensorFlow was released, I have been very excited about what we could do with TensorFlow from R. And hopefully I will communicate that well to you tonight. I've been working for the past 18 months or so with a couple of other folks from RStudio on building R interfaces to TensorFlow, and I'll talk a lot about that work tonight. I'll start, though, by kind of giving you an introduction to what exactly is TensorFlow, kind of define it, what are the core components of it, give you some intuition about what it might be good for. The principal application of TensorFlow, definitely not the exclusive application, the principal application is deep learning. So I'll talk a little bit about deep learning. What is it? Again, what is it? How does it work? What is it useful for, not useful for? And then I'll get into the work we've done in R to let you do deep learning and other types of machine learning using TensorFlow. So first, what is TensorFlow? And you might, some of you might answer, oh, that's a deep learning library that Google has created. And that is true, but it's actually significantly more than that. TensorFlow is actually a general purpose numerical computing library. Actually, its applications go quite far beyond deep learning or even just machine learning. TensorFlow is open source, as I said, and one of the most interesting characteristics of TensorFlow, I think from our standpoint in the R community, is that it's hardware independent. So we in R have been wrapping numerical computing libraries for a long time. The original S language was motivated by wrapping Fortran numerical computing libraries. And we've been wrapping BLAST libraries, which you can see listed there. We wrap the C++ Eigen library. We love wrapping numerical computing libraries in R. The cool thing about TensorFlow is that it's a numerical computing library that runs on all of the hardware and runs well on all the hardware we have today and also potentially on future hardware. So it runs on the CPU and takes advantage of all the CPU cores, takes advantage of parallel processing using SIMD instructions. It runs on GPUs. It runs on a new piece of hardware called a tensor processing unit, which is something that Google came up with, hardware specifically designed to run TensorFlow programs or TensorFlow models. So that hardware independence is really critical. It also supports automatic differentiation, which is used extensively in the deep learning interfaces within TensorFlow. And the whole system was built from the beginning for scale. It was built for deployment. It was built for distributed parallel execution. It was built to work with very large data sets. So it's a numerical computing library that's really, really powerful, interesting, and built to scale. So why should we care? Well, all the reasons I just talked about, a new numerical computing library for us to build beautiful R interfaces to. A couple other things I didn't mention, the optimization algorithms in TensorFlow, the whole system is built with the presumption that all the data is not going to be in RAM. So the optimizers don't require that all the data is in RAM. Most optimizers that we might use, or many optimizers we use with machine learning, have the assumption that all the data is in RAM. That assumption is not there with TensorFlow. And the other thing that I'll get into a little bit later is that when you deploy a TensorFlow model, you don't bring along any R code with that or Python code. It's just deployed against a C++ runtime. So traditionally in R, we'll do exploratory work, we'll build models, and then when we deploy them, it can be a challenge to bring R along with that. The whole model of deployment is that you don't. You use a C++ runtime for deployment. All right, so some of the basics of TensorFlow. What is a tensor? What's flowing? How does it work? What are some uses of it? Tensors, actually, you're all already familiar with tensors, and you use them all the time in R. They're just arrays, specifically multidimensional arrays. So a vector, which is pretty much we all use all the time in R, is a 1D array. A matrix, or is a 1D tensor. A matrix is a 2D tensor. And then R actually supports 3D and 4D and ND arrays using the array function, array data type. 0D tensor is a scalar, which R actually does not have a scalar data type. But you can think of a scalar conceptually as a vector that's always of length 1. So pretty much tensors are what we already use in R to do most of our computation. So that's really nothing new. Some examples of tensors and how they play out in TensorFlow. One of the things I want you to note is that the first dimension is always samples. There's always n number of these things that we're considering. So when we think about vector data, like a data frame, we can convert our data frame to a matrix. That's a 2D tensor. Samples are the rows, and the features are the columns. That's a 2D tensor. So that's very common in R. 3D tensor, a time series would be an example of a 3D tensor, and we do represent time series objects in R kind of in 2D, but if you think about it, there's the features and then the steps, like a data frame, but then in time series, you're actually considering a sequence of observations and how they relate to each other. So that's really a 3D data structure that the model's considering. It's considering multiple steps at one time. Images are an example of 4D tensors. You might think of an image as a 3D data structure. You'd think height, width, and then color channels, red, green, and blue. But in TensorFlow, it's a 4D tensor because you have multiple images. So I'm going to feed 4D tensors, say 10 images, each of which has 3 dimensions. And so the whole tensor itself becomes 4 dimensions. So all the data you feed into these models is one of these. It's a 2D, 3D, 4D, or in the case of a video, that would be like a 5D tensor, because a video is just a sequence of images. So that's just defining the term. Usually when you're actually coding, you're basically mostly dealing with matrices and some essentially arrays that stack multiple matrices together. So what's the flow part of this? What does that represent? Well, TensorFlow models or TensorFlow programs are not like ordinary scripts in R or other programming languages. Actually, a TensorFlow program is a data flow graph. The tensors, the data, flows through the graph, and then the graph has operations in it. The operations are sort of like functions. They're matrix multiplications or additions of bias terms or taking a gradient. So the program is represented as this data flow graph rather than just as a script as you might be accustomed to. And I'll get into why that's actually beneficial in a second. When you're actually working in R, though, typically with high-level interfaces to TensorFlow, you're not actually building the graph directly. I'll explain this code later. This is some R code that basically builds a Keras model, a neural network. And you're just declaring layers of the neural network. There's nothing about graphs or nodes or operations. That is a picture of what the actual TensorFlow graph that's created as a result of this model. Again, you don't usually program that directly, although you can if you want to. There are interfaces for interacting directly with the graph, and more innovative applications of TensorFlow might want to take advantage of that. So what is the motivation for this data flow graph? Why do we have a graph? Well, I can think of a couple other analogs in R of intermediate representations that might make this a little more intuitive. So when you write a Shiny application, you have a set of inputs and outputs and reactives. That is actually effectively a graph of how the inputs and the outputs of your application relate to each other. And when Shiny runs your graph, it can actually be smart about, oh, this input changes, so I only need to execute this reactive and this output. So Shiny is another example of a graph that by Shiny knowing the structure of your user interface can run it more efficiently. When you write dplyr code that works against a relational database, the dplyr code is going to create SQL. The SQL is an intermediate representation of your query, and that is going to get fed to a SQL optimizer that's going to run the query really fast. So the motivation for the graph is basically speed, performance, scalability, portability. So by getting your model into this graph, it actually can be run in parallel. It can be run in parallel across multiple machines. The operations can be compiled in an intelligent way, like fusing together related operations. And then we get this portability attribute where when you deploy your model, it's just running with C++. It's not running with R or Python. So that's kind of the motivation. So that's really at the lowest level what's going on with TensorFlow. And so what are people doing with this? I'm going to get into some of these in more specific detail later. But we have a gallery on our TensorFlow for our website that basically has a bunch of blog posts that write up some different applications. People are doing a lot of deep learning with TensorFlow, which typically might involve some computer vision. It might involve natural language processing, speech recognition. It might involve doing analysis of really noisy time series data. There are people who are doing conventional machine learning things like support vector machines with TensorFlow. So there's lots of things people are doing with it. But because it's a general purpose numerical computing library, there are other applications of it that you may not have thought of. And I'm actually quite excited for the R community to kind of get their head around this and figure out what might be possible. I'll give you one example of this that's already happened in the R community. There's a project called Greta, which is similar in aims to Bugs and Stan. The idea is writing statistical models and fitting them with MCMC. But the way Greta approaches the problem is that you write R code rather than writing in a special language to define the model. You just write regular R code. You can see a comparison of some Greta code and some Bugs code. And then that code actually gets compiled into a TensorFlow graph. And therefore, that code can train on huge data sets, can run fast, can train fast on multiple CPUs and GPUs, can be deployed. This is actually written using the R interface to TensorFlow and is taking advantage of that underlying numerical computing and automatic differentiation to do something that really has nothing to do with deep learning. So hopefully we'll see many more applications like this. So now I want to get into a little bit of what is deep learning and what's it useful for. Should we care about it? Now, later, kind of the motivation for why even spend time on learning about doing deep learning with R. So at the very, very highest level, what is deep learning? It's really, this is an example of a handwritten, grayscale image of a handwritten digit. And we're trying to build a model that will predict what that digit is. So really, what deep learning is I have an input domain, like an image, and I have an output domain, a prediction. I have inputs and outputs, observations, predictions. And I'm going to build a set of, I'm going to change the representation of that image to get closer and closer and closer to my output domain. It's stacking layers together that progressively transform the representation of data until it gets close to the output or the prediction that you want. That's the fundamental mechanic of deep learning. So what are layers? Some of you may have seen neurons and neurons activating other neurons. I'm not going to talk about that at all here. You can think of a layer as just a data transformation function that is parameterized by coefficients or weights. So they're just big functions. Sometimes a layer could have 100 coefficients, and it's going to do some kind of a transformation of the data, and we have to learn what the weights are to do the correct transformation. So it's a geometric transformation parameterized by a set of weights. That's really what a layer is. And when I talk about representations, what am I talking about here? So this is a really trivial example of how changing a representation gets us closer to the prediction domain or the output domain we're looking for. I have a bunch of points. I want to classify predict whether a new point is going to be white or black. By changing the coordinate system, I've made the prediction quite trivial because when I change the coordinate system, now if x is greater than 0, the point is black, and if it's less than 0, the point is white. So you might think of this or know of this if you do machine learning as feature engineering, where you're transforming your inputs or features into ways that are amenable to modeling. And in a deep learning model, the feature engineering is basically learned. We don't do a lot of hand tuning of features before we feed them into the model. Instead, the layers are the feature engineering. So there are transformations that probably aren't this trivial, but sort of transformations like this, again, to get us closer to the prediction domain. So going back to the example of the handwritten grayscale digit, as we go through the layers of the model, we're discarding kind of the appearance of the digit, and we're kind of learning filters that let us see, okay, there's shading, there's an edge, there's a slanted edge. And as we go through the layers of the model, I'll kind of explain a little bit more how this works later. We go from just the appearance of the digit to something that's closer and closer to the actual prediction, which then in the final layer we get. So we're stripping out, we're distilling data by stripping out relevant information and trying to get closer to the essential thing we're trying to predict. So that is where the term deep comes from in deep learning. It's not deeper insight or deeper models. It's layers. It's many layers. You could call it equally well layered representation learning or hierarchical representation learning. Those might be like slightly more precise terms. But it's called deep learning because of all these layers. And in the number of layers I showed 4, there could be 10, there could be 50, there could be 100 layers, depending on the application. So typically machine learning models will tend to have some feature engineering and then 1 or 2 layers. Deep learning has many, many layers. That's why it's called deep learning. And what can we do with this technique, with this different approach to mapping inputs to outputs or observations to predictions? Well, deep learning has accomplished quite a few things I would call in the perceptual domain. So computer vision, image classification, speech recognition, handwriting transcription, some things in natural language processing. Some of these things have been composed together to do things like autonomous driving. So deep learning is able to learn very, very complex functions that we haven't been able to learn with previous machine learning techniques. How is this possible? To give you some intuition, you think about a paper ball. You think about like trying to write a linear equation for uncrumpling a paper ball. It would be really difficult to do that. But if you think about what a human being uncrumples a paper ball, they're just going to do 30 or 40 little simple transformations to pull apart the paper ball until it's flat. And that is, in a way, really what a deep learning model is doing. It's going to learn the sequence of simple transformations to ultimately do something very complex, to learn a very, very complex function. And that's why I think it's worked better on some of these very, very complex perceptual tasks. So why should we care about deep learning? I think there's 2 axes to consider here. One is deep learning plays in domains that we don't do a lot of in R. So things like computer vision and computer speech recognition. There are some reinforcement learning applications, kind of writing models that know how to interact with their environment, play games, or do other things. We don't really do that much in R. We do definitely do some computer vision in geospatial applications and some biomedical applications. So we do computer vision, but we don't do a ton of it. So this opens up, kind of being able to use deep learning from R opens up some new problem domains to us. But I think what's more interesting is to think about, do these tools give us improved techniques for the domains traditionally of interest to our users? Is there data that we have that has very complex sequence or spatial dependencies that's hard to model, too noisy to model? Is there data that we have to do a ton of feature engineering on that may be kind of brittle to get good models out of? So maybe this will provide some techniques for our traditional domains. And I think, spoiler, it might not. It's not proven that these techniques are going to revolutionize any of the things that we traditionally do in statistical modeling and a lot of machine learning. It's definitely proven to be very good, way better than what's come before in these perceptual tasks. But it's a work in progress. But it's a work that a lot of people are engaged in. There are a lot of people kind of coming at, can we use these tools that have done so remarkably in these perceptual tasks to help us with other data analysis tasks? And I'll get into more of that later on in the talk. So before I do that, I want to just describe a little bit the mechanics of how deep learning models are trained and kind of go through that handwritten digit example again in some more detail and talk about kind of the training loop, the basic mechanic. And I'll hopefully in doing this convince you that this is actually a really straightforward mechanism that kind of, once it's been scaled up, can do these really, really remarkable things. So a word first about kind of statistical modeling versus machine learning. I'm not going to get really into this topic, but I think it's important to state up front that statistics is often focused on explanation, on understanding, on kind of figuring out the process by which data is generated. And machine learning and deep learning in particular is really heavily focused on prediction. It's not something that really yields explanations or understanding. And you'll get more intuition about why that is later. So that's a difference. There's a number of links here to kind of read more about that. But it's different than some of us who predominantly do statistical modeling, a different way of thinking about data analysis problems. So let's go back to this handwritten digit recognizer example. This is, I'll actually explain a little more about layers later on in the talk. But basically in R, we're going to define a model that's composed of a set of layers. There'll be certain types of layers we're using. There'll be certain parameters of those layers. We're trying to define the right layers that will be able to learn the task here of predicting a digit. And then those layers will be trained to do these representational transformations that I've talked to you about before. So how does that exactly work? Well, when a deep learning model starts, we have layers and we have weights. The weights are the coefficients that we're trying to learn. At the beginning, the weights are randomly initialized. They actually are complete garbage. So the predictions that you get on the first batch of samples are gibberish. They don't do anything. So we're going to start training our model by having, again, randomly initialized weights. We're going to feed data into the model, and we're going to see how our predictions are. And they're not going to be very good. So what we're going to do is we're going to measure the quality of the predictions by using a loss function. The data that we feed into the model, we actually know when we feed the 4 in, we know it's a 4. And we see what the model, oh, the model predicted a 5. OK, or it thought it was maybe a 4, but probably a 5. So we compare the predictions, and we generate a loss score. And we use that loss to update the weights, to learn the coefficients of the model. And that's the job of an optimizer, which basically translates the loss score into a set of updates to the weights. So this is the basic mechanic. We're going to feed through thousands and thousands of batches of data. We're going to start with weights that are random, and we're going to eventually learn weights that actually cause the model to do what we hope it's going to do, what we wanted it to do. And if you think about this, is a really simple mechanic. And actually, the mathematics behind it are really straightforward. This tweet is from Francois, who's the creator of the Keras library. And he's saying these are not neural, they're not even networks. They're just these chains of functions trained with this really straightforward gradient descent algorithm. So it's a really straightforward mechanic, but it's done all these incredible things. Really, we've created this mathematical machine for uncrumpling these really complicated paper balls. So how does this work? Why is it that this works so well? And actually, the ideas behind neural networks were invented decades ago. So we've actually known about all these things for a long time, and they haven't started working well until very recently. And it turns out that the key to making them work well is to have really large models trained on lots and lots of data. And the reason we can have really large models, there's some algorithmic advances that enable that, but there's also GPUs and modern CPUs that can be used to train really large models. And we have the internet and the digitization of many elements of modern life that have created lots and lots of data. So it's the kind of hardware, algorithmic advances, and more data have actually made these models work. So when I say large parametric, lots of parameters, to give you some intuition about that, the grayscale digit recognizer, a simple grayscale digit recognizer, this is the same one I showed you the code for earlier, has 1.2 million coefficients, or 1.2 million parameters. That's a really simple, it's just grayscale digits. It's not doing much at all. If I build a model that can recognize everyday objects, a model that can look at color images of, and say, is it a cat, is it a dog, is it a table, is it a chair, is it a cloud? That is going to have about 138 million parameters. And that model is trained on 14 million images. So when I say large, that's what I mean large, not like 100, but like 138 million. So that's one of the things that's sort of enabled this breakthrough, these really, really large models trained on lots and lots of data. So what's happened is that there are frontiers now where, especially in computer vision, we've hit new frontiers. We're able to do things that we could never do before, and people are really excited about that. We've started to see some frontiers emerge in natural language processing, natural language translation, and people are working in other fields to see, do these techniques apply? Can we get to other frontiers? Can we find other breakthroughs? So some people are working in time series. Things are going on in biomedical applications. So that's kind of, I think, for us, it's these frontiers. Some of the frontiers are already explored, and we can benefit from those, and some of the frontiers are there for us to explore. So really important this computer vision, this really touched off the kind of intense interest in these techniques across computing and data science. So there's a competition called the ImageNet Challenge that's run from 2010 to 2017, where there's 3.2 million labeled images. You know, it's a vehicle, it's a car, it's a boat, it's a cat, it's a dog, it's a chair, et cetera. And machine learning researchers competed to see who could build the best models for identifying what's in the image. And when they started the contest in 2010, the accuracy was in the low 70s. I think it was 72%. That was the best that machine learning researchers could do in 2010. So in 2012, one team entered the contest and used deep learning, and they beat the entire field by 10.8%. And subsequent to that, everybody started trying to figure out how to do computer vision with deep learning. And in 2017, we were at 97.3%. So in the span of 7 years, we went from 72% to 97%. And that is really what got people so excited, and the reason people are looking, turning up every rock they can, trying to figure out, do these techniques work well for what I'm doing? Same, yeah. Yep. So people are looking hard at natural language processing, and this is one indicator. Could be an indicator that's just a fad, or it could be indicating a fundamental shift, but the graph on the right shows the percentage of deep learning papers at computational linguistics conferences. And it's over that same time period, it's gone from the mid-30s up to 70. So a huge amount of activity there. This paper, these slides will be available. I'll share a link to these slides after the talk. You can find a reference to this paper. Does a roundup of some of that work, and has found that there's definitely progress is being made. That field is not being revolutionized, but progress is being made in a number of areas in natural language processing. One area in particular that huge progress is made is in language translation. Google published this, I think, in maybe in late 2016 or sometime in 2017, their neural machine translation system, which beat their previous phrase-based translation system significantly, and is getting closer to human levels of language translation. So that's another huge win. That's language translation. There are many other things people do in natural language processing, and people are hard at work trying to figure out where else can we do interesting things with deep learning and natural language processing. Some of the same things are going on in time series. Honestly, almost all time series analysis, the conventional time series statistical modeling tools that we have will beat deep learning. In certain areas of really noisy data sets with like overlapping seasonality, people feel like maybe deep learning models could be better. This is a paper that tries to use convolution, which is the technique typically used for doing computer vision, on some time series and compares it to some conventional methodologies. There's another paper that uses a different approach, an autoencoder to try to predict, they're predicting financial, I think, stock prices. So there's research going on and experimentation going on in time series, and this field is not turning upside down because of deep learning. I think in general, if people are getting wins here, they're probably spending several weeks on their model and then getting the win. They're not just, okay, let me try a deep learning version of this. Oh, look, it's better. That doesn't happen. The biomedical field, there's a lot of stuff people are looking at, everything from things like just patient classification, treatment recommendations, even looking into various biological phenomena. This is another paper that rounds up what's going on there. Again, it's not changing the whole field, but there have been lots of promising advances. So again, worth paying attention to if you work in this or related field. This is a very interesting study. It kind of indicates this is a paper that just came out last month. It sort of indicates the very different approach that deep learning models take from conventional statistical modeling techniques. So this is a study that Google and Stanford and U of Chicago School of Medicine and University of California, San Francisco did together. And they looked at electronic health records, which are very messy. There's all kinds of missing data. The data is not well normalized. It's collected in one way at one hospital or geography, and another way in another one. So really, really messy data. Typically, when you want to build statistical models against electronic health records, you have to curate and normalize the data extensively. So you're going to pick out, okay, we're going to pick out a subset of features. We're going to make sure they're properly normalized. Maybe we're going to impute certain data. So this very, very labor-intensive process of kind of picking out the data we're going to analyze so we can actually use a statistical model against it. But in doing that, we're actually discarding a huge amount of data. All that messy data we discarded is gone. It's not part of our analysis. Data like the notes that a physician makes, gone. So what they did was they said, let's take all that data and let's try to have the deep learning model consider the entire medical record. we're not going to clean anything. We're not going to normalize anything. We're going to look at the physician's notes. And the network is going to is going to sort of do its own normalization, do its own culling of the data, and see if it can learn a better model. And in this study, they got predictions that were better than what they got trying traditional predictive models. That could be a straw man, what they tried, but here they found better predictions. If you notice, the people who are on this paper, one of them is Jeff. He's the architect of TensorFlow, so it's not just like anybody can get these kind of results. I think Google tried pretty hard to get these results. But it may be that as this is an example of a technique that we may gain broader understanding of how to apply, and it could change the way we do certain types of prediction. So as you'd imagine, there are many problems with deep learning models. I referred to one of them already, which is that they are black box models. You cannot, a model with 138 million coefficients, you can't look at the coefficients and say, look, we understand this phenomenon so much better. So they're total black box models. They can be very brittle. So if you Google for adversarial examples, there's one you'll probably find which is like a picture of a panda and another panda, and they look identical. But one of them has been doctored to trick the image classifier into thinking it's not a panda by just changing little things. And a human brain would never do that. A human brain has a far more sophisticated set of mechanisms at work, and it can see it's a panda. It's not even a question. But these models can be fragile, so you can trick them easily. And there's ways that are being pursued to kind of overcome adversarial examples. You can think of like in autonomous driving, you want to make sure there's not like an adversarial example of a sign that is misinterpreted. So this is a serious problem for the field, but that's out there. They typically require a lot of training data to perform well. There are ways to do what's called transfer learning, where you can get the knowledge from one model and move it into a smaller data set. I'll talk a little bit about that later, but mostly they require a lot of data, and they're very, very computationally expensive to train. So there are a lot of problems and a lot of reasons that they don't work well for certain things. One of the biggest problems, though, is actually the hype that has emerged around these techniques, driven by some of these big successes in perceptual tasks. And actually, the current generation of tools makes deep learning accessible to people who've never done statistics or modeling. So they can build a model, and they're really excited about it, and it's deep, so it must be good. And it's actually like way more expensive to train than a statistical model, and way worse in accuracy. So we're all going to be trolled by this, in the years ahead. And we can, on the one hand, we could say, well, that deep learning stuff is snake oil, and don't pay attention to it. It probably doesn't work. Or we can try to say, well, let's have a more balanced dialogue about where this can be used and how it can actually be made better. I think that's the thing to do, because in spite of the problems, it's really useful. And you can see at Google, they came out with TensorFlow in, the line here says Q3 of 2014. And it's just the use inside Google has skyrocketed. They've found uses for it in many products and many applications. So I think we got to try to help deep learning find its appropriate place in the domains we work in, rather than just say, oh, there's so many things wrong with it, it's not worth spending any time or bandwidth on. So I want to talk a little bit now about the work we've done in R to let you build deep learning models and use TensorFlow from R. So we have some very high-level R interfaces. You've seen a little bit of that already. We have low-level interfaces to enable kind of new applications like Greta. And we have some other tools to help with your workflow. So, and hopefully we've also invested quite a bit in sort of educational resources so you can learn more about how this stuff works. So there's actually 3 sets of high-level APIs to TensorFlow from R. There's the Keras API, which is this high-level interface for neural networks. There's the Estimator API, which is sort of the classic linear regressor, linear classifier, classic machine learning. Those APIs almost look like R modeling functions. And then there's the Core API, which is this low-level access to the graph, which was used for Greta and can be used for other kind of innovative applications and research. And this then sort of ends up, there's actually 7 R packages that give you interfaces to TensorFlow. There's one for each of those interfaces. There's a package called TF datasets that deals with giving you access to very large data sets from TensorFlow models. And we have some supporting tools for deployment, experiment management, and doing cloud training. So I'll talk a little bit about all this in a minute. So the Keras API, we're going to actually talk quite a bit about that today. That's the high-level API. Again, you're just saying, these are the layers I want. and then you fit your model from there. Again, I'll drill into this more later. That's really the kind of the preferred API. There's this estimator API that, again, it looks like R model, like traditional R modeling. You say, I want to create a linear regressor or a linear classifier. You can actually do neural networks with this, but they're specified at a really high level. You say, well, I want 6 layers, and I want them to be this width. It's not anything like the granularity you get with Keras. So really the way to do neural networks is with Keras, and the way to do some of these more straightforward models is estimators. And then the core API actually you're actually computing directly on the TensorFlow graph, way lower level. You can see here I'm actually defining my loss function explicitly. I'm doing my training loop explicitly. So again, I don't recommend people use this interface unless they want to, interact directly with the graph or do things like Greta. But we have this interface for people who want to use it. So let's talk a little bit more about Keras, kind of step through an example and talk about some of the different components of the Keras API. Before I do that, I want to just describe a little motivation about why Keras. And actually, Google is now emphasizing Keras, especially in the last six or 9 months, as the preferred interface to TensorFlow. If you look at this is on the left, kind of web search interest in deep learning frameworks. And you can see in the last year or 2, the interest in TensorFlow and Keras has just taken off. On the right is, interestingly, this is actually from about a month ago. There's a website called Archive, which has all the research that's done in deep learning is generally published to Archive. And there you see a lot of TensorFlow, but you see a huge amount of Keras. So it's really interesting that Keras is sort of really popular, easy to use API for practitioners, but it's also used quite a bit by researchers. So it's quite flexible and quite adaptable. So that's why we put a lot of energy into the R interface to Keras. So I'm going to walk you through a Keras training script, the different components of it. And this will be for this application of recognizing handwritten grayscale images of handwritten digits. The first step is always going to be pre-processing, and that's going to basically be getting your data, whether it's sitting in a CSV file or it's sitting in a directory full of images or sound files or text documents, and somehow getting that into tensors. You're going to turn whatever your raw data is into vectors, matrices, 3D arrays, et cetera. So there's a pre-processing step. And then there's a step where you define the model by basically saying, these are the layers I'm going to use in my model. And it's not the process of the model definition. It looks like, oh, I just have to type in these 5 layers. It ends up being the case to get a good model. You're going to play with these layers like hundreds of times. So it's not a lot of code, but it is a lot of effort to get a model that works well. Which layers, stacked how, with what parameters, really determines the quality of the model. So after you've defined the model, you compile the model by basically saying, what loss function do I want to use, what optimizer do I want to use, and what metrics do I want to collect to judge how my model is performing. Before I go on, I want to make one comment about this model compile statement. You notice that I'm not assigning the result of that statement back to the model. I'm actually modifying the model object in place. And that is not typically how things are done in R. Typically, R objects are by value. You pass an object in. If changes are made to it, a copy is returned. Keras models don't work that way because they're actually these complex acyclic graphs of layers. Layers can appear in more than one place in a model, and those representations are shared. So they're objects that are modified in place. So I say model compile, and that actually changes the model. That's just, you may not quite understand how this code works unless you know that piece about the objects being modified in place. All right, so we've defined our model, we've compiled our model, and now we're going to train our model by calling fit. Fit basically takes the data, the x and y, and then it has a few other parameters. It says, how many samples at a time am I going to give to the model? In this case, I'm going to give 128 samples at a time. How many times am I going to traverse the input data set? Again, I have to look at the data many times over to get a good model. So here I'm going to say, look, scan through all of the data 10 times. And then the other thing I'm going to specify here is that hold out 20% of the data for validation. Because if you have a deep learning model that's big enough, it will just memorize your data. So that's one technique. If you let it do it, it'll just memorize your data. That is not a model that generalizes well, a memorization. So what we do is we hold out 20% of it, and we constantly test our model against the held out data to make sure it's not just memorizing the input data. So that's what that is. So we fit the model. You can see, we notice we return a history object from the fit, and we can see that we can plot the history. We can see how did accuracy and loss change over all the epochs of the model's training. This is a really good model because accuracy and loss are converging. Validation is the same as the validation accuracy is the same as the training accuracy, so we're generalizing well. But a lot of times this looks nothing like this. You'll see overfitting. You'll see your validation data getting worse as your regular training accuracy gets better. So this is a diagnostic tool that you use to figure out how well training is going and how well your model is working. When you're done with that, there's an evaluate step. There's yet another bit of data that's been held out, data that the model, again, has never seen before and you haven't used for tuning parameters that you can use to assess the model. And then you can generate predictions just like you do. There's a predict method, there's predict classes. Generate predictions the way you normally do in R from a model. So I'll give you a quick demo of how that looks inside RStudio. This is the same training script. And I'll start by loading the data. The MNIST data set, the grayscale images, that actually comes with Keras. So I just load that up. And then I take my data and I reshape and scale it in various ways until I've basically got, as you can see, I've got a few matrices that I'm going to feed into the model. So that's, you can see over here, I've got my matrices I'm going to feed into the model. And then I define the model, compile the model. I can actually print a summary, as I showed before in some other slides. What are the layers? How many parameters? This model has 235,000. So it's a less complex model than the other one I showed you. And then I'll fit the model. And as I fit the model, we're going to show you real-time metrics, which is really important because a lot of times models training doesn't go well. You start to see the validation accuracy get worse. The model's plateaued. So it's really important to get real-time feedback about how the model's doing as it's training. And you can usually then you'll interrupt the model and try something else. Once you get the history back, you can plot the history, and that'll give you that same plot. You can actually get a data frame back and do your own plots. Evaluation, I showed you on the slide, and then generating some predictions. So that's the basic workflow. This is a pretty simple Keras training script. They can get a lot more complicated than this, but this is kind of demonstrates the basic mechanics for training. And this model does actually perform at about 98% accuracy on handwritten digits, which is pretty good for such a simple and straightforward model. All right. OK, so getting a little more into the Keras API, we've talked about layers. There's the art of building these models is basically figuring out which layers to use and how to compose them. And so there's actually 65 different layers. I'm not even going to bother enumerating all the layers. There's 65 different layers that are built into Keras that do different things. And you can actually also create your own layers. You can write custom layers. Just to give you a sense of categorically the types of layers there are, to give you a flavor of some of the differences. There are dense layers, and again, this is the classic 1970s neural network of perceptrons and all connected. One layer of neurons connected to another layer of neurons to another layer of neurons. They're kind of the staple of neural networks, and even more complex models typically will have these dense layers at the bottom. They're kind of the staple workhorse basic neural network layer. There are convolutional layers that are typically used for computer vision. The idea behind convolutional layers is that there's patterns of data inside an image or some kind of other data structure that are location or translation invariant. So like edges or shadows or at a higher level like eyes. And if you see an edge or a shadow or an eye in one part of the image, you should be able to recognize it in other parts of the image. So convolutional layers basically learn these filters, and the filters are then kind of slid over the whole image to look for these things. So once a filter has learned to find an eye, if it sees an eye in the upper right-hand quadrant and then sees an eye in the upper left-hand quadrant, it can still recognize it. So again, these are used a lot of times for finding patterns in computer vision applications. But as you can see, people have used them for time series and that sort of thing too. Recurrent layers are basically layers that can maintain state. So if I'm looking at a set of input data, the current set of input data, I'm trying to make a prediction based on that. But in the case of sequence data, time series data, or text data, it also matters what I've seen before. So recurrent layers are layers that can accumulate kind of a vector of state information. They can learn a vector of state information, and then that's used to condition the predictions to the next layer. So those are recurrent layers. Again, used in time series, used in a lot of natural language processing applications. Embedding layers, for those of you who do natural language processing, you'll recognize this. The idea is that if you look at text, You could look at text as just a classification. So I have the word dog and I have the word cat, and they're just two different words, and there's 10,000 different words, and they're just two of them. Or you could learn a representation of the word that reflects that the fact that there are semantic relationships. Like cat and dog, they're both house pets, they're both mammals. So embedding layers try to learn richer representations of kind of categorical data, in this case like text data. And so there are embedding layers that can actually learn those vectorizations as you train, or you can actually take pre-trained word embeddings that have already been developed using other techniques like word2vec, and you can load those into embedding layers. So that just gives you an idea of like 3 of the different types of layers there are. And really the trick of building these models is to recognize what kind of problem am I solving and what kind of layers will make sense and what composition of those layers will make sense. So the next step is compiling the model, and I've talked about this a little bit before, but really what's happening here in Keras is that when we compile a model, we're converting the layers into a TensorFlow graph. And we're then saying we have the layers converted into a graph, and then we take the loss function, we add that to the graph, we take an optimizer, add that to the graph, and then we say what metrics do we want to collect, and we add that to the graph. So this is really just building the graph that we're going to execute. The Keras API has a whole bunch of loss functions. You can actually write your own loss functions, as you might expect. So different tasks require different loss functions. They have a bunch of different optimizers, some of which work better for different types of data and different tasks. They have a bunch of different metrics, built-in metrics, and as you'd expect, you can write your own metrics that let you evaluate, the efficacy of your model as you're training it. All of this that I just talked about is articulated much, much better in the Keras for R cheat sheet. You don't need, again, to get this link down, because I'll give you a link to the slides. This is also easy to find on our TensorFlow for R website, which I'll give you a link to as well. But the cheat sheet is gives you a great 10,000-foot view of everything that I just talked about and the syntax for it. So what are some examples that actually using R to solve these problems with the tools, the Keras tools that I just talked about? We actually have a gallery on the TensorFlow for R website. And the gallery is a bunch of in-depth blog posts that basically talk about problems, the motivation, the data set, how we trained the model, what went right, what went wrong, some intermediate data visualizations for diagnostics of the model, speculation about how we can improve it. So they're really in-depth blog posts about different application areas, all using the Keras for R interface. So I think once you get the basics, once you learn the basics, this is a great place to go next to kind of learn about deeper application of the techniques. The first one I want to talk about is actually, I talked about this idea of transfer learning, where you can actually train on a very small data set and still get a model that performs really well. This is an image classification example that was trying to predict whether an image is a dog or a cat, and it was actually trained on only 2,000 input images. And the reason it could do that is it actually took a bunch of the model that was used for that ImageNet data set that has a lot of knowledge about shapes and objects and things that are related to dogs and cats. It also knows about other objects as well, vehicles and household appliances and everything. But we're able to build a model on only 2,000 input images using this transfer learning technique. And this article kind of describes transfer learning. There's another article that gives us sort of a primer in the different ways you might do time series forecasting. This was actually weather time series data trying to predict temperature. And we talk about using these recurrent layers I mentioned, stacking recurrent layers. There's a thing called bidirectional recurrent layers that try to look at the data in both forward and backward. So this is a good primer on some of the techniques you would use in time series. This is a really interesting example of trying to classify peptides to figure out in cancer immunotherapy, when we introduce cells to treat cancer, how they're going to bind to existing cells. So this is it's a classification problem, looking at the peptide, saying how's the cell going to bind. And this compares using a regular feed-forward neural network against a random forest, and also tries to use a convolutional model, but the convolutional model ends up not being better. And so there's a little discussion about, well, what to actually get a better result. What other things can we try to get a better result? This is an example of trying to look at a data set that has 300,000 credit card transactions, I think only 400 of which are fraudulent. So a typical logistic regression might have trouble picking up enough signal in the 400 fraudulent transactions. This is using a technique called an autoencoder to try an alternate way to try to figure out which transactions are fraudulent. This is a natural language processing example that tries to take, it's a data set of 400,000 pairs of questions from Quora and tries to figure out, are they duplicates? This also demonstrates putting a Shiny application as a front end to a Keras model, which is actually quite straightforward. Another example using a basic feed-forward neural network to predict customer churn. And this demonstrates a couple other interesting things. It demonstrates using a package called Lime, which I'll talk about in a minute, that while we can't look at a deep learning model with millions of parameters and say this is how this phenomena works, you can actually take individual predictions and you can figure out what features contributed to that prediction. So this is a dashboard that's actually also built with Shiny that says for this customer, what's their % risk of churn, and then what attributes of that customer actually contributed to that prediction. And then finally, an example from learning word embeddings, which I talked about before. We've got a database of Amazon food reviews, and this is an example of trying to learn a richer vectorized representation of words than just classifying the words, which then can be used later for parsing and sentiment analysis and things like that. I want to address a little bit this issue of explainability, because again, these models have really no explanatory power when you look at all the coefficients. But there are ways to try to understand how a prediction was made by a deep learning model. This is an example of a model that's predicting what's in the image, and it's saying it's an African elephant. You can actually look at the gradients of the intermediate layers in the model, and you can draw a heat map out of that, juxtapose that heat map over the image, and you can say what parts of that image actually contributed to this prediction. Similar to what I talked about with Lime, where you can say, for an individual prediction, what features contributed to it. And when you're using these models to do things like, approve or deny credit or make a medical recommendation, it's really important. Even though the model itself, it's functioning as a black box, it's important to be able to highlight, well, these are the reasons why. These are the things about the situation that caused the model to go one way or the other. So kind of back to this deep learning frontiers, there are many fields of inquiry, I think, where people are going to take a run at improving the state of the art using deep learning. Most fields that we work in now, unless you're in computer vision or maybe natural language processing, traditional statistical methods are going to be cheaper, they're going to be more accurate, they're going to be more reliable, easier. Yet there are these frontiers, and that's very compelling for a lot of people to say, well, could we do better? Could we analyze data that we're not currently able to analyze? So I think you could have a few different approaches. You can really take a wait and see approach and say, well, when I see that it's really obvious in my field that people are using deep learning a lot, I'll use it then. You could follow research, and not just formal research, but also things lots of people are on the internet experimenting and writing blog posts about things. You could follow that and kind of evaluate it and say, do I want to try that in my work? Or you can even do your own research and try to say, I want to really get my head around how all this stuff works, and I'm going to be one of the people who's trying to find that frontier. So there's a lot of different approaches. I really want to highlight again that in a lot of fields, other than these kind of staples, it's really not there yet. And if you go looking for these big wins, it might be really hard to find them. I think, what does it look like if you are trying to approach that frontier? I think typically when people succeed with building a deep learning model, it can take a matter of weeks to actually try all the different things, the different architectures, the different hyperparameters required to get the model to work well. I think when people start using these tools, they don't have an intuition, and then that intuition is sort of developed over time. They tend to need a lot of compute power, and you tend to need tools that help you manage experiments and get the most out of the compute power that you have. So it's hard, and in many ways it may be the wisest thing may be to wait until you see people in your field succeeding with it to try to get involved in it. But it's really interesting stuff to play with and try out. So I think a lot of people are tempted and go and spend the time on it, and I think a lot of good things will come out of it. We've built a bunch of supporting tools to help with this. One of the most important tools you need to have, especially if you're doing convolutional networks or recurrent neural networks, is a GPU. These models, convolutional and recurrent models, are really slow on CPUs. So there's a lot of different ways to use GPUs. If you have a current, recent high-end NVIDIA GPU on your local workstation, you can use that. Most people, many people, vast majority of people don't. And there's other ways you can use GPUs in the cloud in various ways. That's probably the easiest way, or you can go buy a box that has a GPU. That's another way to go. So the cloud is a great way to do this because you can work locally on your laptop, and then when you need a lot of training and compute power, you can get it from the cloud. We've done a couple things to enable that. We actually have an RStudio server with TensorFlow, Amazon Marketplace image. It's free in that you only pay for the Amazon compute cost. But this actually has everything pre-installed: RStudio, TensorFlow, the NVIDIA libraries, Tidyverse. Got everything pre-installed. So this is a great way to play around with the GPU with very little investment, fixed cost investment. There's a CloudML package that lets you do training on Google's CloudML using their GPUs, and that's more like a batch submission type service. So there's different ways to use GPUs, and our website covers that in detail. The TensorFlow for our website covers that in detail. We have a package called TF Runs. I'm not going to actually spend very much time on this, but it's used to manage training experiments. So just at the highest level, you're going to run hundreds of training runs trying to figure out what hyperparameters are the best, what model structure is the best. So instead of sourcing the R script that runs the training, you call this training run function, and then we collect data on every run. We actually know all the outputs of the run, what the metrics of the run were, what the model was, what the source code was. And so this is a way of managing all your runs, and you can view reports on the runs, you can compare different runs, you can establish flags for runs and use that for doing grid searches. So TF Runs package is really good. Once you get past the learning stage, you're actually trying to tune a model. It's a really good way to go about doing that. The TF Deploy package has tools for deploying models. Again, I said when we deploy a TensorFlow model, there's no R or Python code. It's just C++ code. So we have tools for working with that. Again, I'm not going to go into that in a lot of detail, but the process is you export your model, and then once you have an exported model, you can serve it with like a web server that gives you a REST interface to it. You can serve it using an open source project from Google called TensorFlow Serving. You can serve it with RStudio Connect. You can serve it with CloudML. So it's sort of this sort of binary format, again, sort of language runtime independent that can be served in lots and lots of different ways. You can put them inside a Shiny application pretty easily. And one of the cool things is that, again, this idea of a model serialization that's not tied to a language means that these models can actually not just run on servers, they can run on embedded devices, they can run, there's Apple iOS has a thing called CoreML. You can actually feed Keras models directly to CoreML. So you use R to train a Keras model, and then you deploy it on an iPhone with no R on the iPhone. There's a library called Keras.js that lets you deploy these models into JavaScript, into the browser. So there's lots going on with taking these models and making them deployable in lots of places. So that's really, really interesting too. And so we'll try to build tools that keep up with that and let you do all of that easily from within R. So biggest things I think to take away, think of TensorFlow. Yes, it's a deep learning library, but it's also this numerical computing library that's hardware independent, that's really fast, that we can do a lot of stuff with in the R community. Deep learning's done a lot of great things with perception, and I think in some fields it's going to make an impact. Some fields sooner, some fields later, some fields not at all, but I think it's going to make an impact. And probably most importantly, R now has the best deep learning tools, the Keras and TensorFlow out there. We have a great set of APIs for them. We have a bunch of supporting tools. So if you want to get involved in this stuff and you use R, there's really wonderful support for that now. A lot of the stuff I talked about tonight, you can find at the TensorFlow for R website. Easy to remember, tensorflow.rstudio.com. Again, I'm going to give you a link to these slides, so you'll have that link there. So that's a good place to start, and the gallery I talked about and documentation for all the packages is all there. This is important. As Jared said, there's 2 books that I would recommend reading if you're interested in this, and they're very, very different books. The deep learning book on the right is actually kind of the definitive work in the field in terms of the concepts and theory behind deep learning. The book has no code in it at all. It's all concepts and math. The Deep Learning with R book was actually written by the creator of the Keras library. And I worked with him. I didn't write, my name is on the cover, but I didn't write any of the prose in the book. I just adapted. He wrote the original book, Deep Learning with Python, that was used with Keras, and I basically adapted it to the R interface to Keras. So it's Deep Learning with R. This book is a really good conceptual introduction to deep learning. It actually has no math, all code. So it's everything is done with R code. So one has no math, all code. The other has no code, all math, depending on how you learn and how you like to approach problems. Read them in whatever order you think is appropriate. But I think if you read these two books, you will know just about everything you need to know to get started. So thank you very much. The slides that I just went through are available at the URL I have here. I'll keep the slide up. And if you are interested in this, we have a blog, TensorFlow for R blog, and that's where we post announcements about packages and other software releases, but we also post all those gallery entries, the examples. Those are also going on the blog too. So if you want to kind of stay up to date and see what's happening and see what kind of interesting examples people in the community are coming up with, I would urge you to visit and subscribe to the blog. So thank you very much.
Questions? First one's over here.
Thanks for an awesome presentation. I'm interested in the GPU and the interaction of these libraries with the GPU.
Yeah.
At times, the memory management needs to be tinkered with.
Yeah.
Are the CUDA DNN libraries exposed? Where's a good place to look for that?
Yeah. The TensorFlow uses CUDA and CUDA DNN under the hood. And typically what you do is you run like NVIDIA diagnostic tools to see like what your memory and GPU utilization is. So you can't interact directly with CUDA. TensorFlow is doing that, but you can see how the model is taking advantage or not taking advantage of the GPUs. And one of the things that can happen is if you get a model that's training really fast, then the bottleneck can actually become the ingestion of the data. And that's one of the things that TF datasets package addresses, is to try to parallelize, like I'm reading and pre-processing the data and I'm training at the same time. So you can have a model that's like only using 20% of the GPU because all the time is spent in pre-processing. It's not getting data to the GPU fast enough. Yeah, that's right, yeah.
I'm interested in the autoencoder that's
Yep.
for detecting fraud.
Yep.
So first of all, does it mean that you're taking basically data and feeding it through and trying to match it to itself?
Yeah. So the autoencoder is like learning an alternate representation of the data. And so I think the way that one worked is that it took the non-fraudulent transactions and it learned this other the auto-encoded them to another representation. And then it fed data through and it looked for like prediction error. And it said like if I have high prediction error indicates it's probably not like the things I auto-encoded in the first place and therefore is fraudulent.
So I'm curious, first of all, that's the only concept I know. There are other ways of fraud detection or of anomaly detection. And my second question is, you mentioned you have to do a lot of experimentation with various type of parameters.
Yes.
But, and I don't know, maybe you cover that in the book. Where do you even start? Like, what determines what kind of dimensions of the problem? Determine what is even a reasonable.
Unfortunately, I think there's a lot of it is like witchcraft. A lot of it is really people just try stuff. There isn't theory. And in fact, what you I've heard talks of people at Baidu saying the way we train people is we just give them like hundreds of examples, and it's like a cockpit simulation. They just try things. So it's not, I think in a given field, it might get narrower than that. Like in computer vision, it's like, okay, these kind of layers with these kind of parameters tend to work well. But like for something like this, I don't think there's not a theory or literature that says this is how this is done. There probably will be, if there's anything to find here, there will be in a few years, but there isn't right now. Yeah, they're bleeding edge, that's right, yeah. Yep.
any comment on the speed using TensorFlow using R versus TensorFlow using Python?
It should be the exact same, because it's really just using all the same libraries. It's the exact same. Yeah. Yeah.
Anyone else?
Yeah.
Well, I guess I was wondering if you could elaborate on that. If it's working. So I guess if we start off with TensorFlow and kind of Python universe,
Yeah.
you showed some really good stuff in RStudio with the
Yeah.
chart.
Yeah.
Like, what would be the key selling points to use RStudio and how do you
Yeah. I think the key selling point is that you like to use R for doing data analysis. You like the whole R ecosystem. You like working in RStudio. You know, that's really, it's because you prefer R, and now you can do all the same things in R that you can do in Python. I think if you already prefer Python, there's not a clear motivation, right? It's not, because it's really the same exact library, just with here's a Python skin and here's an R skin. So.
Hello. Just to return to the question of all architecture and Python selection, is that something that could be learned itself?
Yes, in fact, yes. Do you already know the answer to this? Yes. So yes, in fact, if you Google has a thing called AutoML, which literally it starts from no model, and it learns the whole model, the layers, the hyperparameters, everything. And they actually have, so they're doing that, I think, they have a service called AutoML now that I think it does it for computer vision, but that is, some variation of that is probably the future. I mean, all the machine learning engineers sitting and trying grid searches of things and witchcraft, this and that, that's probably not the best way to approach this. It's probably some kind of combination of your intuitions that you develop over time and then machines looking in the space of models.
So Café has a concept of a model zoo,
Yeah.
where you can take already defined architectures like AlexNet, et cetera,
Yeah.
and pull those in.
Yep, yep.
Is there something similar here?
Yes. So there's so Keras has a thing called Keras applications, which are pre-trained models. So you'll see them. It's called Keras applications. Those are almost all computer vision models, and there's a bunch of them. Those are the easiest to use. TensorFlow has also, I don't know if it's called a model zoo, but they have a big collection of models. Those are harder to use, honestly, from R than the Keras models, and Keras has ported most of the interesting models. So yes, with Keras, there's something similar. I don't know if it's comparable to the depth or breadth of the model zoo that Café has, but it's there.
So you offer these three interfaces to TensorFlow, Keras, the
Yep.
CF estimator, and the core API.
Yep.
So from the core API, which I have most experience with, you kind of patch in an interactive session and directly evaluate the TensorFlow.
That's right. That's right.
It's useful for debugging and everything.
Yes.
Is there a way to do that from within the higher level interface?
It's a good question. So, you know, when you're writing a custom layer, you're basically, so if you're just composing layers, really you just have to train the model and see what happens. If you're writing a custom layer or a custom loss function or custom metric, then you're basically writing Tensor, the same sort of code that you write in the lower level interface. You're basically doing the same thing, but inside a custom loss function or metric or optimizer. So those, yes. The debugging of those, I think, will get better with, there's a thing in TensorFlow coming called eager evaluation, which basically will, one of the problems with the graph is that it's all deferred. So in R, nothing's deferred. When you add do a matrix multiplication, it happens and you see the result. There's a thing coming to TensorFlow called eager evaluation will give you the same semantics. So then when you're building like a custom Keras layer or loss function, you'll just be able to call it like a function and test it and see what it does. So I'd say when you're building the custom things, it's very similar to that lower level interface. So.
Anyone else? Another one over here.
Thanks. Great. Again?
What's the model?
You killed the button. Mike, do you have another mic?
Thanks. So what was the
Project you described the deal with
Don't hold it. Don't push it off. Don't push the button.
Did they kill every So most of the projects you were talking about deal with data both the same class. So you have like visual
image,
or you have like expression data or something.
Yeah.
Or EHR.
Yeah.
How do you combine data from different types?
Yeah. So I'll tell you the way you basically can build. I didn't show this, but in Keras they have this concept of a multi-input model. So you can have a model that actually takes in some vector data, some image data, some sequence data. And so again, I showed you the sequential model, which is just like a stack of layers, and that's most common. But you can build a graph of any level of complexity. So you typically will have multiple inputs, and then they'll get down to a certain point, and then you'll concatenate them in some way, and you'll maybe weight the concatenation of them. Ensemble built in, yeah. So like you'll get all the data, and then you'll flatten them and concatenate them together. So yeah, that's how you do that.
So you kind of process different types of data, your factors,
yes.
the numerical, whatever.
Yeah.
You process them separately. You build them.
Yeah.
For each.
Well, it's one model that has multiple inputs. So I showed you feeding input data like here's the X data. You could pass a list of data. So you could have a model that has 3 heads, right? It's got this takes an image, this takes some vector data, and this takes like a sequence of text. And then they all, you feed them in a list, and then they all, at some point, you can actually have multi-outputs as well. So you can have multi-inputs and multi-outputs. So let's say you have a single output. At some point, those inputs are going to get concatenated together somehow. You're going to weight them, or you're going to do something that says, OK, I've got these different factors. Well, what happens is to standardize it, you typically like to standardize them, you like just flatten them. So you've got a tensor, and it's 2D or 3D. You just flatten it out into a bunch of numbers and then concatenate them together. It's like a big soup of numbers. And then you feed it through the dense layers after that. So you're not, it's not like you're writing a program, you're saying, I'm very explicitly, like I'm going to normalize them, I'm going to put them together. You're just going to like slam them together and put some weights on them, and then let the network see if that lets the network build good predictions.
2 more questions. If we're both in the back of you, Joanne.
Can't hear you. Yeah.
So when the convolutional network model is more efficient than a traditional statistical model, how do you feel that still the traditional statistical model is more relevant, and the automation convolutional is giving you more accurate result than the statistical model?
In computer vision, you're talking about? Yeah, in computer vision, I think people are using these kind of models. I don't want to say exclusively, but this is like really the predominant way people build computer vision systems now. It wasn't 5 years ago. But that's not necessarily the case in like natural language processing. In natural language processing, it's still mostly traditional things, and then people are experimenting with this. So
I'm more worried about is that like in future, traditional statistical model will be irrelevant.
I don't think so. Not from what I can see, and people are trying really hard. I think the deep learning performs really well with like really, really messy data that's hard to encode, that's hard to feature engineer, has a lot of noise in it. That's the kind of data that it does well on. But if the data is like vector data that's like well structured and understood, it's almost impossible to beat, the tools that we already have. And deep learning doesn't really add much in those cases. So.
Last one.
You kind of answered part of my question. I was going to ask you. I was going to ask you, where do you see deep learning having trouble in the future?
Yeah.
You kind of addressed that. Well, I guess another question I had was, you see different domains having a different proportion of the sample being validated?
You mean yeah? People play with that validation split depending on the type of data that they're, that varies depending on what the type of model you're building, like how much data you need to hold out.
Is that becoming standardized by any chance?
I don't know. I'm not sure. I don't know.
All right, thank you very much. A big round of applause.